This video is going over section 3.3, power functions and polynomial functions. For those of you that are watching these, the reason we don't do section 3.2 is because it's on quadratic functions, which are parabolas. We don't really use anything specific. It just kind of goes over the quadratic formula, vertex formula, which we never use, and factoring. So it's all a review. If you are weak on the quadratic formula or factoring, definitely email me, contact me, and I will give you some extra practice. But there's nothing else we really need from that section. So the topics in this section, we'll talk about a power function and then some important things about them. They're called their degree, coefficient, and end behavior. You might actually be familiar with degree and coefficient already. You may not be familiar with the end behavior part. This is definitely the absolute new thing for most people. And then the second part, we'll talk about polynomial functions. We'll see how it's related to power functions, what their degree is, what's called their leading coefficient, and end behavior. And then the last little thing is very important when it comes to what we're going to try to do in this chapter, which is, if we're looking at a polynomial, finding all of its zeros or x-intercepts, and that's really the start of it at the end of this section. Okay, so begin by defining what a power function is. Right, if a is a real number and n is a non-negative integer, so it's 1, 2, 3, 4 positive whole number, then I guess we can include 0 because I'll have an example of that. But then a power function f is written as f of x equals a times x to the n power. A is called the coefficient and n is called the degree. All right, so in a lot of ways, the way you think about a power function is it's a number times x to a power. And the power cannot be anything but 0, 1, 2, 3, 4, and so on. It can't be a fraction, it can't be negative or decimal. All right, so for each of the following, we'll just kind of look at them, determine if it's a power function. If yes, state the degree and state its coefficients. All right, so number 1 here, f of x equals negative 3x to the 5th. Is this a power function? The answer to that is yes, because it is a number, negative 3 multiplied by x to a positive whole number power. And the degree is the exponent. And the coefficient is negative 3, the number. If there's a negative sign, make sure you include negative because it's going to be very important whether it's negative or positive. Right. So number 2, the example, j of x equals negative 2. What you'll notice here is that there's no x. Really, that's going to be thought about as x to the 0 power, because anything to the 0 power is 1. So when we have something that only has a number there, we can think about it as x to the 0 power. Right. But one thing that's usually a reminder at the beginning of this course, anything to the 0 power is 1. That's a good one to talk about. For some of you that go on to calculus, you'll find out that's slightly a lie, but it has to be set up in a specific way. For now, anything to the 0 power is 1. So I'm just going to think about writing this as negative 2 times x to the 0. And if we ask the question now, is it a power function? The answer is yes, because we have a number multiplied by x to a power that is a whole number and not negative. So it's yes, the degree is 0. Right, the degree of a whole number is just 0, and the coefficient is the number itself, -2. Number 3 here, just to have like a messy kind of number, we have k of x equals pi times x squared. Is this a number multiplied by x to a positive whole number power, or not negative? And the answer is once again yes. Pi, even though we can't really write down what it is, we can only round it. It is a power function because pi is a real number. So the degree is the power, which is 2, and the coefficient is pi. So these last two here, you'll see just these are the common ones that you don't want to say yes they are a power function, because they are not. 3 over x, this is not a power function, right? The main reason is simply you can't have an x in the denominator, because x in the denominator means it's a negative exponent. And we cannot have negative exponents for power functions. Right, now for a reminder on exponent rules, remember if we have no power written, it's just 1. If we want to bring something from the bottom of a fraction to a top, we put a minus sign on its power. So this is the same thing as 3x to the -1. And we can see more clearly now it is not a power function because the exponent doesn't work. So this is not a power function. The exponent is negative, which is bad. And then the last example here, m of x equals the square root of x. Now the fact that we don't have a number here is fine because it can just be thought of as 1. The main reason this one is bad is because the square root is the same thing as the 1/2 power. Right, so remember when we have radicals, if we have an n on the radical and the thing inside is on the power m, then as an exponent it's x to the m over n power. And when it comes to radicals, when we don't write a number here, it's actually 2. And on the inside, we don't have a number written there because it's actually 1. So anytime you have a radical, it's a fraction exponent. The numerator is the exponent inside. The denominator is the exponent, or not the exponent, but the number on the radical. But this is not a power function because the exponent is a fraction. And it needs to be a not negative whole number. Right, so what we're going to see for the first 90% of this chapter are things built on power functions. You won't see any negative exponents. You won't see any radicals. That's not what we're studying in this chapter. So the thing that's going to be pretty new for most of you is the end behavior, also sometimes called the long run behavior of a power function. The notation might seem a little weird. I have all this highlighted because I think it's all very important. You should also write this stuff down because this is what you're going to see in the problems. But I'm just going to read through it. The end behavior, sometimes referred to as long-run behavior of a function f of x, is equivalent to being asked, what y value does the graph of y equal f of x go to as we move to the left and to the right? Don't worry, we'll have an example of this. But for the notation, as x goes to negative infinity, think about the number line or a y-axis, xy plane. If we're saying x goes to negative infinity, really what we're saying is what happens as we go to the left. That's what I have outlined here. If x goes to a negative infinity, if we're going to the left, what does the y value go to? This arrow means goes to. And if we have x going to positive infinity, x going to positive infinity is to the right. So if we want to ask the question, what does y go to as we move to the right, it's going to be written as x arrow infinity, x goes to infinity, f of x, or y goes to what? And in general, this is a hard question to answer, but with power functions, it's pretty straightforward because of the way they work. So I'm going to make a little chart down here and I'll show you how you can see this on your calculator. Sometimes it's nice to just practice this enough and not have to graph them in your calculator, but you can always check these in your calculator. Right, so it says if f of x equals a times x to the n is a power function of degree at least 1. We're not going to have degree 0 here. We're not going to have just numbers. Then the end behavior depends only on the coefficient, whether it's positive or negative, and the degree, whether it's even or odd. All right, so what I want to do is kind of make a chart here to explain how you figure this out and why it works the way it does. Right, so on the top here, I'm going to talk about a, the coefficient being positive or negative. That's what a is representing. So whether a is positive or negative. And then the other thing it depends on is whether the power or the degree is even or odd. So what I'm going to start is by writing just one example of these and look at the graph because all the graphs will mimic the same shape. Okay, so if a is positive, we can always think about it as 1. And if n is even, we can use 2. So this is pretty much asking for y equals x squared. Now, hopefully you are familiar with that. You remember what the parabola looks like. If not, just graph it in your calculator, which we'll do in a minute. But it's that U shape. And if we ask the end behavior questions for this, as we go to the left, what does y go to? As we go to the right, what does y go to? Well, as we go to the left, y goes to positive infinity. And as we go to the right, the y value is also going to positive infinity. That's what these arrows are for. So as we go to the left, as x goes to negative infinity, y goes to positive infinity. And as x goes to positive infinity, as we move to the right, y also goes to positive infinity. Now this is for x squared, but it works as long as your coefficient is positive and your degree is even. So we'll actually go ahead and do an example in my calculator here. I have a TI-84 on here, but if I graph, let me make sure I'm in the right mode. If I go to my y equals menu, if I pick any number, positive number, and then x to any even power, I'll pick 6. If you want to graph it, you can hit graph. If you're not in a standard window, you can hit the zoom button and 6 and it'll put you in the standard window. You'll see that parabola shape. The only thing that changes when the powers are different, but they're still even, is that it gets a little steeper. So you can see as we go to the left, this is going to go up to positive infinity. As we go to the right, this goes up to positive infinity as well. I can graph another one here, 5x raised to the second power, which will be in red, and then maybe one more just so we can see it. 8x raised to the 16 power. And so we can see what's happening. Even though they all look a little bit different, they're all doing the same thing. As we go to the left, they're all going up. As we go to the right, they're all going up. Power functions are never going to come back down. Okay, that's one thing that's very important. If you can see that it's going up or see that it's going down, it's going to continue doing that. All right, now if our power is even still, but a is negative, we can think about y equals negative x squared. And if you remember what the negative sign does to a graph, it flips it over the x-axis. It's going to look like this. And what this is saying is, as we go to the left, the y goes to negative infinity. As we go to the right, y also goes to negative infinity. As we go to negative infinity, as we go to the left, y goes to negative infinity. As we go to the right, y goes to negative infinity as well. And once again, you can do examples in your calculator. I can go to y equals, I'm going to get rid of all this, but pick any negative number. You can just do negative x squared like we had for our first example. Negative 6x to any even power. And you can see that they'll both do that same thing. One's going to be steeper than the other, that's fine. But as we go to the left, they both go down to negative infinity. As we go to the right, they're both going to continue going down. And now when n is odd, you can think about y equals x, because that's a line and you know what it looks like if a is positive. Any even power works. Odd power works, just like the evens. Y equals x, that's a line slope 1. I was supposed to pass through the origin, I missed a little bit. But this one, as we go to the left, it goes to negative infinity. As we're going to the left, it's going down to negative infinity. And as we go to the right, as we go towards positive infinity, it's going up to positive infinity. But once again, this works for any positive a, any odd power. So I can do y equals x. I can pick any positive a, any odd power, 9. I can even do a weird number like pi. It's positive times x raised to the 5th power. They're all going to do the same thing as I move left and right. Now the shape's vastly different when you have a line and when you don't. But as we go to the left, right, they're both all going down to negative infinity. They're all going down. As we go to the right, they are all going up. And once again, with power functions, they're going to keep going up and keep going down. You have the picture in front of you. And then the last one, finally, when n is odd and a is negative, we can think about y equals negative x. that is either thought of two ways. You can think about flipping this over the x-axis, or slope with -1. It's decreasing. And they're all going to have this shape. So as x goes to -infinity, as we go to the left, y goes to +infinity. And as x goes to the right, y goes to -infinity. So that's a handy thing to remember. It's also helpful to remember that if you graph these things, power functions, you can see what's going on. For those of you taking calculus, it's probably a good idea to try your best to remember this and understand it, because you will use it pretty early on in that class. All right, but we'll go down to the examples. The examples are basically either looking at the chart or graphing them and understanding what it's saying. The number one, let f of x equal -14x to the 11th power. And we want to know what happens as we go to the left, as x goes to -infinity. And as we go to the right, as x goes to +infinity. And you can do this one of two ways. Right, you can plug it in your calculator, graph it, understand what's happening. You can have it sort of remembered in your head, the chart. Either one is good. All right, I like to use chart, but that's because I'm so used to this. I'll graph the example as well just to confirm what we do. But the two things we want to look for here, we have a negative coefficient, a -a, and an odd power 11, or odd degree, whichever one you like to write. It's probably better to use degree just to practice the word. But if it's negative and it's odd, it looks like y equals -x. As we go to the left, it's going to go up to +infinity. As we go to the right, it's going to go down to -infinity. Right. Now, once again, I would like to mention that you should keep track of that. But if you want to just graph it to double check yourself, it doesn't hurt. We want to graph y equals -14x to the 11th. And we see exactly that. As we go to the left, it goes up to +infinity. As we go right, it goes down to -infinity. All right, now on the homework, you just want to make sure to type in infinity. You can actually hit the 0 button, meaning the letter O twice to type infinity, or you can find it if you click on that up arrow in the homework. All right, I just have a second one here to, really hammer in the point of what we're doing. As x goes to a -infinity, as we're going to the left, what is happening? As we're going to the right, what is happening? And the two things we're looking out for are coefficient as positive, and our degree 8 is even. So if our coefficient is positive and our degree is even, it's going to look like y equals x squared. Right, positive for the 1, 8 for the even, so x squared. And this is really what you would want to do on the test, unless if you fill out this whole chart, which I wouldn't necessarily recommend. You want to just draw a little picture of what you know it's going to look like. Then we can see as we go to the left, it's going to go up to +infinity. As we go up to the right, it's also going to go up to +infinity. But as far as in behavior for power functions, that is it. We are going to use them very heavily when we do the in behavior of polynomials, which is next. All right, so the next part of this section, polynomial functions, degrees, leading coefficients, and one thing that we will not really use a lot of yet, but is going to come into place, I'm just going to mention it now, is something called the constant term. The definition of a polynomial is typically pretty overwhelming, just the way it looks. If you're not familiar with it, a polynomial function f of x can be written like this. We have a with a subscript n times x to the n power plus a with a subscript n minus 1 times x to the n minus 1 power, and so on down to a2 times x squared plus a1 times x plus a0. Now, one thing to mention here, the easiest way to think about a polynomial, each thing is called a term. So a n x to the n, a n minus 1, x to the n minus 1. Each of these are called terms between the pluses. And each of the terms is a power function, meaning everything that you see in a polynomial linked by a plus or minus is a power function. So as long as everything we see in a polynomial is a number times x to a positive power or a non-negative power, we're good to go. Right. Now, the important definitions of a polynomial. The degree of a polynomial is the largest exponent. It doesn't necessarily have to be in front, which we'll see. It is the largest exponent. The degree is very important. The leading coefficient is also very important. The leading coefficient is the coefficient of the term with the highest power of x. Meaning, if you have found your degree, the number that's being multiplied by it, that's the leading coefficient. The constant term is the term, that's a typo. It should be, say, term without your variable. So if you have f of x and you don't have an x in a term, then that's its constant term. And we'll see sometimes that's 0, but it can be anything. And one thing I will stress, which we'll see in the examples, the powers of x do not need to be in descending order. You don't have to have them all. You might have a lot of things missing. You just need to not get used to everything being perfectly written. Right, so we got a couple examples here. It says, for the following functions, determine if they are polynomials. If they are, state the degree, leading coefficient, and constant term. Right, so one thing we want to look at is every single one of these a power function? And the answer to that is yes. All the x's are raised to positive whole number powers. We have number by itself, which is fine. We know that means it's degree 0 term. And all the numbers that multiply them are real numbers. So yes, it is a polynomial because every term is a power function. As long as it's a polynomial, then it makes sense to ask the question, what are the degree, leading coefficient? I'll probably just go ahead and abbreviate leading coefficient LC, not to write all of it out, and then the constant term. The degree is simply the largest power of x. If we look at all the powers of x here, the largest power is 7. The leading coefficient is always the number multiplying the largest power of x. X to the 7th is nothing's written there because it's really being multiplied by 1. The leading coefficient here is 1. And the constant term, if there's a number by itself without the variable, then that's it. The constant term is 1. So this is a polynomial because every term is a power function. Its degree is 7, its leading coefficient is 1, and its constant term is 1. Next example here, 18x to the 4th plus ex to the 5th minus 2x to the 9th over 3 plus x. Is this a polynomial? Well, we ask ourselves, is every term a power function? And once again, that answer is yes. All the numbers here are real numbers. There's no i's. And all the powers of x are positive whole numbers. We got x to the 4th, x to the 5th, x to the 9th, and x to the 1st. Right, the 3 down here is fine because it's just part of this coefficient. So yes, it is a polynomial. For the same reason above, every term is a power function. And we want to answer the same 3 questions because it is a polynomial. What is the degree? What is the leading coefficient? And what is the constant term? And we want to remember the degree is the largest power of x, not the power of x in the front. If you look through the powers of x, the largest power of x is 9. So the degree is 9. The leading coefficient is the number multiplying the largest power of x. So if we're looking at x to the 9th here, what's multiplying it? We have 2 over 3. But we've also got this negative sign here. And you do have to include the negative sign. That is because the definition of a polynomial has a whole bunch of pluses in it. So if we're talking about coefficients, we have to take negative signs with them. We got negative 2 over 3. And the last question, constant term. You'll notice that there's no terms without x here. So really that we can think of having a plus 0. Our constant term is 0. The constant term is never going to be d and e. So if everything has an x in it, the constant term is 0. All right, so the last example here is this thing, a polynomial f of x equals x to the negative 1 plus x to the 5th plus the 6th root of x, or minus 6th root of x rather, minus 31. And the answer to this is no. All right, we have 2 terms that aren't power functions. All you need is 1, but just to reiterate the common examples, these 2 aren't power functions. We saw the reasons before. You cannot have a negative exponent. So the first thing, x to the negative 1 is bad. And the other thing that we saw before, radicals are fraction exponents. So the 6th root would also make this not a polynomial. But just to practice this again, the 6th root of x would be, really we have x to the 1 power inside, we'd have get x to the 1 over 6. And it cannot have a fraction exponent. All right, so the end behavior of polynomials, this is what you have to be far more careful about. The end behavior of polynomial functions, in general, if you try to graph these, it's pretty challenging because you don't know what's going to happen with the polynomial. Right. Polynomials, as we'll graph this one just so you can see it, they go up and down. They kind of look wavy. but you don't know when you graph it if it's going to turn around going from down to up on your calculator or not. And you can only zoom out so much before you can't even see the thing because it's too small. All right, so to determine the end behavior of a polynomial, all you do is look at the term of the polynomial with the largest power of our variable. If you do that, it will have the same end behavior as that power function. So the first example here, f of x equals x to the 7th plus x to the 5th minus 3x squared plus 1. Our leading term here, the term with the largest power of x, is x to the 7th. What this is telling us is we're going to have the same end behavior as y equals x to the 7th. Right, what happens is all these lesser powers don't matter because x to the 7th, when x gets really close to negative infinity or really close to positive infinity, really, really big, really, really small, it's much, much bigger than the others. All right, so it's going to have the same behavior as y equals x to the 7th. And now it's just a matter of how you figure that out. If you want to graph this, you can. If you want to point out the two things and kind of make a picture on your own, you can do that as well. We have a positive coefficient. And we have an odd degree. Right. So y equals, we're thinking about y equals positive, odd degree, I'm thinking about y equals x. And the graph of y equals x is the line with positive 1 slope. Okay, so as we go to the right, the y is going to go up to positive infinity. Oops. And as we go to the left, here, it's going down. And so as we go to the left, as x goes to infinity, f of x or y goes to negative infinity. As x goes to positive infinity, the y value goes to positive infinity. Once again, you can graph this, but you might not actually see the answer. You have to graph or use the power function. So we're going to go ahead. I'm going to graph both so you can see both. The first one I'll graph is just the power function, y equals x to the 7th. And the polynomial was y equals x to the 7th. I don't have it memorized. Plus x to the 5th. Minus 3x squared. And I can't remember if it was plus. Whoops. How did I do that? Minus 3x squared plus 1 or minus 1? Plus 1. All right, so I don't actually know what this red graph is going to look like. It might give us the correct picture. It might not. The blue graph is going to give us what we want. All right, so actually for this example, the red graph would give you a good picture, but you don't actually know that's going to happen. So we can see from the blue picture that's going to go down to negative infinity. As we go to the left, it's going to go up to infinity as we go to the right. In general, if you graph the polynomial, sometimes it will work, sometimes it won't, and you just don't want to take that chance. So once again, you look at the end behavior of the power function. All right, number two, we do the same thing. We want to figure out the end behavior of f of x equals 18x to the 4th plus ex to the 5th minus 2x to the 9th over 3 plus x. We look at the leading term, which is negative 2 over 3 x to the 9th. Remember that negative sign, it's very important. So it's the same end behavior as y equals negative All right, let me not forget the other numbers. Negative 2x to the 9th over 3. I want to point out the same things here. The coefficient this time is negative. And the degree is odd again. All right, so that's going to look like y equals negative x. Which looks like that. Now, as x goes to negative infinity to the left, y is going up to positive infinity. And as we go to the right, as x goes to positive infinity, the y value is going down to negative infinity. Right, so if we go ahead and fill out our answer over here, as we go to the left, it's going to go up to positive infinity. As we go to the right, it's going to go down to negative infinity. And once again, I'm not going to graph the polynomial this time because I really don't know what it will look like, if it'll work or not, and I don't want to confuse watching the video. I'm just going to graph the power function to double check. Oops. So I want to graph the power function just to check my answer. We got negative 2x raised to the 9th divided by 3. And we get exactly the picture we expected. As we go to the left, it goes up to positive infinity. As we go down, as we go right, it goes down to negative infinity. Right, so for the most part in this section, end behavior is the main thing. You definitely don't want to forget this stuff with the polynomials. The fact that the only thing that matters is the highest power of x is very important, or the leading term. All right, now one thing that's pretty important, like I mentioned at the beginning, is relating the degree of a polynomial and the number of real zeros, x-intercepts, roots. They all have the same name. It's one of the main things we study. And for the rest of this chapter, we will often be discussing real zeros of a polynomial. And zeros are often referred to as roots or x-intercepts when talking about graphing. So I might go between one and the other. I might sometimes say roots. I might sometimes say real zeros. I might sometimes say x-intercepts. I'm talking about the same thing. And you just have one theorem here that is very useful because it'll tell you when you actually are getting to the point of figuring out the real zeros when you're done. So it says, let f be a polynomial with degree n, then the number of real zeros of f is no larger than n. All right, so what this theorem tells you is if you have a particular degree of a polynomial, the maximum number of x-intercepts, if you graph it, is that degree. It doesn't tell you how many there are. So there could be a lot less, there could be none, even though your degree is 100. It just tells you the most you can have. Right, so for the following polynomials, I have a couple examples here. State the maximum number of real zeros each may have. Well, this first one here, as long as we write down the degree, it's going to be the same thing. The degree is 9, that same polynomial we've been looking at. So the maximum number of real zeros is 9. Now, if you graph this and you can manage to figure out where all of them are, you might not see 9. You probably won't see 9, but it's the maximum number. The second example here, I wanted to throw in a second one because we can actually graph this one to sort of explain what this is saying. F of x equals x squared plus 1. Its degree is 2. the maximum number of real zeros or x-intercepts or roots is 2. I'm going to use x-intercepts this time, just to go between the different words. Okay. Now the reason I want to bring this up is to stress what this theorem is saying. It does not tell us we have 2 x-intercepts. In fact, for this one, there's going to be 0 because this is the graph of the parabola shifted up one. It's never going to have an x-intercept. And if we go ahead and just graph that y equals x squared plus 1, no x-intercepts, parabolas open up or down forever. It's never going to turn around. It never hits the x-intercept. But you do want to be careful on these questions. You do not want to do anything else besides look at the degree. It's just telling you the maximum number it could possibly have.